because I like packed this lecture with a lot of stuff. So here's a video of a hopper doing a backflip trained with human preferences. And so we'll have a lecture on reward function inference next week. And yeah, so the cool thing about this task is that it's like hard to specify a reward, and they did it just by like comparison. Yeah, that's what this is showing. Okay, so where we are in the class is we've covered three types of RL algorithms: policy gradient, dynamic programming, model-based RL, and we were trying to find a unifying framework across these three types of methods. And we were trying to use probabilistic inference as our tool to do so, right? And so the hope was that we want to find one framework where you just turn a knob and it gives you these three different types of algorithms. And to do so, we were kind of trying to go from a hard notion of optimality, things that do maximization, to a softer notion of optimality, because people are not optimal, and you might not always want to be optimal. You might want to be like probabilistic, leaning towards optimal, so noisily optimal, right? And so we tried to build a soft notion of optimality. And to do so, we're going to use this framework of probabilistic graphical models, right? And so a graphical model is just a convenient way to encode a joint probability. And so looking at this graphical model, you can encode the joint as a product of conditional probabilities that only depend on the variance, right? So you have P of A times P of B given A times P of C given A times B given BC and E given D, right? And so you can think of a graphical model as just a way to encode a joint probability. And once you have this encoding of joint probability, what you want to do with it is answer queries, right? So you want to answer queries on like, if you had some evidence, like what is the likelihood of particular random variables? And so you want to say, if the example I gave last time, if it's wet on the ground, what is the likelihood that it will? Right? So things like that. What we're going to ask is like, if assuming that we were optimal, what is the likelihood that an action was taken? So we're going to like try and task reinforcement learning as inference, and that's why it's called controlled inference. Right? But the point of probabilistic inference queries is that you want to answer these posterior queries. So like find out what the likelihood is of some random variable given some evidence, right? And so if you're in the table, you can do this with variable elimination, right? So you can say that, I think we talked about this last time, but essentially if you have, let's take the simple example, P of B given C comma E, right? You can like write this as P of, write this as P of A, B, C, D, E with A and D summed out, right? Divided by P of A, B, C, D, E with B, A, and D summed out. You can just use Bayes' rule and conditional probability. So like summing up A and D will make this the joint of B, C, E. Summing up B, A, and D will make this the joint of C and E. So you'll have P of B, C, E divided by P of C, E, which gives you P of B given C. Right? And so in a tabular setting, these are just matrices, with matrix multiply, row normalize, and you will get what you want, right? So it's like there's more efficient technique called variable elimination, or you can just like enumerate everything. It's something. So doing this in a table is easy. Doing this in any continual space is hard. And so what we're gonna show today is like a bunch of techniques to do this in continual space for a particular graphical model that corresponds to control, right? And so that's the framework we're going to use. So we're going to ask the questions, what does it have to do with RL? We're talking about reward maximization or soft maximization. How do we cast that as an inference problem? And then how do we like tractably solve it and show that approximations to these inference problems give us these different model-based RL, model-free RL, Q-learning type outcomes, right? That's what we're going to do. Fair warning, this is like the hardest lecture of the whole course. And so we might have to go slow and struggle through it a little bit, but because I mean, this is the first time I'm teaching this, and so we'll work through it together. But a lot of it is going to be me writing on the slides. Okay, great. So let's start by trying to figure out what graphical model we want to optimize for. So this is the typical graphical model of like a Markov chain, right? Or a Markov decision process, almost. So you have states and actions transitioning to next states, right? and you have, let's say you have a likelihood of ST plus 1 given ST and AT, right? That's your transition dynamics. Those are the true conditional probability distributions in this model, right? So P is like a true conditional probability distribution. It's like, what is the likelihood in the environment of going from S and A to ST plus 1, right? And then this P of AT given ST, it looks like a policy, but it's not a policy. It's what we're going to call our action prior. So it's like, if you had like no other information about what you're trying to do in the environment, what is the prior that you would take this action at this state, right? So it's like, if I was not trying to be optimal, if I just trying to do random stuff, like what is the prior of taking that like action, right? And so a lot of the times in these frameworks, we'll just like set this to be uniform, right? Or a constant. And so we're just going to ignore it. But essentially, it's like in a Bayesian sense, it's like a prior probability that tells me if I wasn't trying to do anything goal directed, like what actions would I be likely to take? And it's okay to like set it as uniform because you don't have any priors about what actions you would take, but you could inject priors on what actions you would take if you know. Like if you know that you want to take smaller actions more than larger actions, you could inject a prior. So this is our initial graphical model, right? But if you look at this graphical model, it doesn't have any notion of reward, right? There's no notion of reward. There's no notion of optimality. There's no notion of like control in a goal-directed way here, right? Sorry, I forgot to record. Oh, no, I'm recording. Good. So there's no notion of any goal-directed behavior here, right? It's just saying, how does the world transition? And so if we want to do control, then we need to introduce a notion of goal-directed behavior or optimality or reward, right? And so what we're going to do is something which is a little bit wonky, but we're going to like, oh, sorry. Okay, so what we're going to do is we're going to add in a series of optimality variables, okay? And these are going to be binary variables. So at every time step, you're going to introduce an optimality variable. I had a little typo, but these also depend on action. Or a draw O. Basically, optimality variables are binary variables. Okay, so you can either be 0 or 1. And at every time step, you're going to introduce an optimality variable. So this like capital OT, it looks like observation, but in this case, we're in a Markov decision process, not observation, it's optimality. So we're saying that like it's a binary variable, which is 1 if you're optimal, and 0 if you're not optimal. And so it's going to be like a convenient mathematical, it's not the most intuitive thing in the world, but it's going to be a mathematical tool we'll use that'll help us derive all our other algorithms, right? But we're like essentially adding in, we think these as auxiliary variables, we're adding into our Markov chains. And we're going to make these dependent on reward, and that's going to let us do control, right? But these are just binary random variables that you add in to your graph, which can be either 0 or 1. And OT only depends on SC and AT. So OT is independent of everything else given SC. And so just like we had conditional probabilities for dynamics and the action prior, you're also going to have a conditional probability for your optimality variable, okay? So your optimality variable can be either 0 or 1. And it's going to have a conditional probability distribution, P of OT given ST and AT, right? Yes. So all we've done is we've said we're going to add in these binary random variables. They can be 0 or 1. And if you're 1, optimal, 0, suboptimal. And the conditional probability distribution, we're going to define as dependent on the reward. Yeah. Yeah. So it's a little bit tricky. We're going to like, when you're thinking of behavior being optimal, you need to not be optimal just at that time step. So don't think of it as like S and A are optimal. Think of it as like we're defining this random variable, and we're going to say let's not think about optimality for a second. Let's call it something else. And it can take values 0 and 1. And the behavior is optimal when all of the time steps are 1. So like, because it's not independent, you want things to be optimal when all of the time steps are 1, right? So you can think of optimality not just as OT being 1, but the likelihood of O0 to capital T. And so because in RL you can't just say you can't just say like this is optimal without making these things optimal, right? And so what we're going to do is we're going to introduce these random variables. Let's I think it's a little confusing to call them optimality. Let's call them like auxiliary variables for now. Okay. And the auxiliary variables can take in values 0 or 1. And an optimal behavior is when you have all of the auxiliary variables set to 1. And a suboptimal behavior is when you have anything else. Right? And so you can think of optimality, like true optimality of your entire behavior as auxiliary variables 0 to capital T all equal to 1.
Are all these optimality variables equally important, or we have some?
So what you want is you want the joint of all of them to be 1. And so they're differently important in the sense that they're like rewards might be different, and hence they might be differently important the same way that different conditions are different. But like basically optimality at one time step is not a thing we care about. We only care about optimality at all times. So in that sense, they're equally important to the overall goal.
Well, things about the probability of OT given STAT.
Yes.
So it's like,
Yes, OT equal to 1.
yes. Okay, so when it
Yeah.
the probability that it is optimal is like.
Yeah. So it's saying that for a particular ST and AT, right? The likelihood that you're going to have OT equal to 1. So you can think of this as like a binary like decision table, right? And so you have OT equal to 0, OT equal to 1. This is going to be X per R. This is going to be 1 minus X per R, right? And so at every time step, you're going to have an OT given ST and AT, and it's going to be this table with likelihood of optimality equal to 1 equal to X R, and OT equal to 0 is equal to 1 minus X. Yep. And so we'll get to like the intuitive meaning of this in a second, but mechanistically, all this saying is like add a set of auxiliary variables that can be binary and define their conditional probability distribution in the graph, which only depends on the pairs, right? As is binary, so it's 1 is going to be X bar, 0 is going to be 1 minus X. And we'll get to why we do this in a second, but does that make sense from a mechanistic standpoint? Do we just like how we change the graph, right? All we do is we added the auxiliary variables, we define the conditional probability. Now, like what do we need for this thing to be well defined? XR. It is like R is like yeah, so right? So you're just gonna make sure that your rewards are. You're just gonna, because you can scale everything by a constant, we're just gonna subtract the maximum reward. So all rewards are negative or non-positive. Okay. And so we've introduced these optimality variables, right? And we've defined what they are. And now let's try to intuit what we want from them, right? And so what we want from them, oh man, I'm sorry, I forgot these arrows. But what we want from them is, as I was saying earlier, you can think of these as like auxiliary variables, and the like event of optimality is when all of the auxiliary variables are 1, right? So you can almost think of there being like a mega random variable, and that random variable is 1 when all of these are 1, right? And it's not 1 when any of them are. And so what we're trying to figure out is like, and so a behavior is optimal when you see that like the corresponding O 0 to capital T is positive. And so that's going to be our graphical model, right? And then we're going to ask the question, how do we think of decision making in this context? We've defined a graphical model. Currently, it has nothing to do with control. It's just a graphical model with some transition. It has some similar things. It has, transition likelihoods. It has these things which are X bar. It has some action priors, but it's like not really control yet. Right? It's some nebulous. And so what we're going to do to kind of bring this to match control is we're going to ask, the question is like, what is the likelihood of a trajectory when you observe it to be optimal, right? So if you're observing that you are optimal, what is the likelihood of a trajectory? And so it's saying that like you observe that the agent is goal directed, it's trying to like soft maximize reward. Then in that case, what is the likelihood of a trajectory? And so let's like work through in this, so we can answer this question in this graphical model, right? As we can say that if we, and as you remember, a trajectory is just a series of states and actions, right? Till ST and AT. So that's a trajectory. And the optimality variable 0 to t is just optimality 0, optimality 1, blah, 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 till optimality. Yeah. And so this posterior split square we want to answer, right, is saying what is the likelihood of a trajectory given that we observe every time step to be optimal. Okay. And so we're going to use Bayes' rule. So we're going to say if you have, P of y given x, it's equal to, it's like it's proportional to P of y times P of x given y, right? And so we're going to have P of t given optimality is proportional to P of t times P of optimality given t, right? Just like Bayes' rule. And now P of t is just going to be the likelihood of P of S naught, A naught to ST, AT. Yeah. And because we saw that like optimality only depends on the S's and A's at the current time step, right? You can write this joint, or this thing is just this guy. And this thing is just the product of P of OT given ST and AT across all the time steps, right? So all we've done is we've said, what is the likelihood of a trajectory being what is the likelihood of a trajectory given you know the agent is trying to be optimal? And then we're saying that's the likelihood of a trajectory from the prior times the likelihood of optimality given a trajectory. Yes. And so likelihood of a trajectory given the prior is going to be basically likelihood of the initial state times likelihood of the transition dynamics times likelihood of the action prior, right? And the likelihood of optimality given a trajectory is just the product of the likelihood of optimality being one at every single time step, right? Because our graphical model tells us these things are independent. So if you have probability of optimality from 0 to t given S0, A0 till ST80, you can just decompose these because they're independent. You can decompose them as the product of P of OT given ST and AT for t equal to 0 to capital T, right? Just from your graphical model. And so what we've shown here is that the likelihood of a trajectory given optimality is true is the likelihood of a trajectory given optimality times optimality given trajectory, which is the likelihood of a trajectory times that P of OT given ST multiplied over multiple different time steps, right? Now, let's write this whole thing as P of t, and then you substitute this guy back into here, right? And now you have like the product of a bunch of exponentials, right? Which is going to be the exponential of the sum. So product of exponentials, you just sum up the thing inside the exponential. And so what you get is it's like the likelihood of a trajectory from the prior weighted by the exponential sum of rewards, right? And so what it's saying is that the likelihood of a trajectory being observed when you're saying things are optimal is the likelihood of the trajectory from the prior times the exponential sum of rewards. Right? And so imagine that like the rewards were extremely high for the optimal trajectory and really low for all the other trajectories. This would just become like an indicator, which is 1 at the best trajectory and 0 everywhere else, right? But the rewards are not scaled that way. And so you'll have like some soft distribution over like the mode will be like the best trajectory, and then you'll have some likelihood over trajectories with decreasing rewards, right? And so it kind of satisfies our notion of soft optimality because it's saying that things that have higher return are higher likelihood, the things that have lower return are lower likelihood.
What was the reason for expanding Peter?
There was no reason. I realized that. Yeah, no, you're right. I like worked through it. I was like, oh, I shouldn't have done that. That was a good guess. Yeah.
Why the choice of the exponential distribution?
I think it's a convenient choice. Oftentimes when you're dealing with things like divergences and so on, like logs and exponents show up. And so this choice just makes everything work out well. if you show the different, like we're going to use scale divergence in a bunch of places, if you show the different divergence, you choose a different.
So it seems like it's not just the return of the trajectory, but also ability by the probability of the trajectory.
Yeah, so you can kind of think of this like, this is like, imagine that you had a trajectory where you like teleported through space, right? Like basically that's going to violate the dynamics, which means that the likelihood is going to be really low here. And so what it's trying to do is like it's trying to downweight things that are inconsistent with dynamics, right? Because you're like measuring the likelihood of all possible trajectories, including infeasible ones, right? And you're just saying like, this is like the likelihood of something being consistent with the dynamics. And this is like the reward, right? So you can think of this as like dynamic consistency, and this is reward. And with stochastic dynamics, it's likelihood, but like the easiest way to think about this is if it's deterministic dynamics, this is 1 for consistent things and 0 otherwise. Okay, so what we've done here is we've shown that under this graphical model, if we try to find the likelihood of a trajectory given everything is optimal, it corresponds to a notion of soft optimality, saying that find trajectories that are dynamically consistent and their likelihood is proportional to their sum of rewards, right? And so it's not max, it's soft max, right? Because one way of thinking about this is like, imagine that we had like divided this by an alpha, okay? And then you drop the alpha down to like really. And what's going to happen is that when you like have an exponent, like the largest element gets scaled the most, right? And so if I like think of it that way, if I send alpha to 0, this will become a max, right? And if I set alpha to something that is not 0, then it's going to become a soft max, right? So one way of thinking about soft optimality in this context is that this thing is just like weighting things proportional to the exponential return. And if you take the temperature and drop it down to 0, it becomes a hard max. And so you can easily interpolate between things that are like soft maxes and things that are hard maxes by just changing the temperature. Or like, in this case, you would like scale the rewards by something. Yeah. Is that parsing? Ish. So let's recap what we did, right? Because otherwise we're gonna be lost. We started with this notion of soft optimality, right? We wanted to get to this. We want to get to some soft optimality notion where it's not just max or not max, right? So we started with this graphical model for control. We added these auxiliary random variables, right? We call them optimality variables, but a trajectory is truly optimal only when all of them are 1, right? They're binary random variables. Their likelihood of being 1. So whenever I use this, I mean it's a shorthand for optimality equal to 1. Right? So their likelihood of being 1 is x bar. The likelihood of being 0 is 1 minus x bar, right? And the trajectory is called optimal when all of these auxiliary variables are 1. And so we started with this auxiliary, this augmented graphical model, and we said that if we ask this query for inference, we say, what is the likelihood of a trajectory given that we know everything is optimal? We saw that it corresponds to a notion of soft optimality, right? And so we said, this gives us like a soft maximization framework rather than just a hard maximization. Yes? Any questions?
Sorry. Does that mean that?
Yeah, but you can always subtract the max. So it shouldn't affect things meaningfully. Because like RL like scales with additive constants. Like it shouldn't change the best policy. Okay, so big whoop, we did this. It doesn't tell us how to get policies. It doesn't tell us how to act in the world, right? We just like threw together some math and we showed that this gives us soft optimality, but I want to act in the world, right? And so the question we want to ask is, what do we do with this thing, right? And so we're going to try and think of 3 different things in 3 different lectures. In today's lecture, we'll try to derive soft RL algorithms, model-based, model-free, policy-graded, all of them, from this framework. The second thing you can do is you can derive soft inverse RL algorithms. So inverse RL algorithms say that given optimal data, can you find the best reward to explain that optimal data? And so we'll show that like an elegant framework for inverse RL can be derived from the same thing. And then lastly, like a lot of the algorithms for transfer learning, like across different problems, they rely on this like maximum entropy type idea or like control as inference type idea. And so we'll get to that later in next week, no, next to next week. Yeah. And so those are the use cases, right? We define this mathematical framework. Now we're going to use it to derive soft RL algorithms. Next week, we'll derive soft inverse RL algorithms, and then we'll talk about algorithms for transfer, right? That's the point. Yeah. Okay. If we feel convinced this is the point, let's start by thinking about how we derive soft RL. So in an RL algorithm, the fundamental entity is the policy, right? The policy tells you how to act in the world. And so far, we haven't really talked about policies. We've talked about optimality and transitions and an action prior, but we haven't talked about policies. So what is a policy in this case? We're going to say that an optimal policy corresponds to a posterior inference query. So you don't have to do any maximization explicitly. You just have to answer a posterior inference query. And the posterior inference query we're going to ask is what is the likelihood of a particular action AT times 50 given a state ST and that all of the future time steps are optimal, right? So intuitively, you can think of it as given that you are acting optimally in the future, what is the likelihood of taking a particular action AT at a state ST, right? And so this, we're going to argue that like this thingy is equal to like pi star from all the previous lectures, right? So we found the optimal policy, whether that is with policy gradient or actor critic or model based. And in all of these cases, we're going to argue that the optimal policy corresponds to this posterior inference query or the soft optimal policy. And so it's saying, intuitively, it is saying that assuming that we were optimal, like what is the likelihood you would take that action? And that is kind of your soft optimal policy. And we're going to like show that all RL algorithms that we talked about so far can be derived, or most can be derived as particular approximations to this posterior inference query. Yeah, no question? Okay. Okay, so what we're going to like, so the point I want to make here is that you're not doing a max. You're just solving a posterior inference query. And we're going to show that it implicitly does something that looks like the soft max, right? But the optimal policy pi star is just this posterior, or soft optimal policy is just this posterior inference query. Now, we just like, remember, if you remember graphical models, we, you know, when we did A, B, C, D, E, we could do, okay, yeah. When we did A, B, C, D, E, we wanted to answer B given C, E. It's like the same type of query. It's just asking the question, what is the likelihood of this action AT, given that you know state ST? So it's like this guy, given that you know this, and everything else in the future is optimal. Right? And so whenever I say, oh, T to capital T equals 1, that means like all of them are. Okay. So that's what we're going to try and compute. We have AT given ST and future optimality. And we're going to show we can derive all our RL algorithms just by figuring out how to answer this posterior inference query, right? So if you're in a table, if like states and actions were tabular, then we just make a big table and like add a bunch of rows and you'll get to the answer, right? But we're not in a table, and that's what's going to make everything a little harder. So any questions? Are we just confused? Yeah. So the point is we constructed this graphical model. That is the definition of the conditional probability. We show that it corresponds to soft optimality. We want to answer this posterior inference query. And so if optimal policies are posterior inference, let's try and answer the posterior inference query, right? So let's do Bayes' rule again, right? So you can say this is we have AT and future optimality given ST divided by future optimality given ST, Bayes' rule, right? And because if you notice in this thingy has AT, ST, and all of the future optimalities, but it does not have any of the future states and actions, right? And so what you have to do is you have to construct a joint with all of the future states and actions and then marginalize out all of the future states and actions, right? So it's saying that like, if I wanted to like truly expand this, right, the similar thing that we did in posterior inference, if you remember, we constructed the joint of A, B, C, D, E and we summed out the irrelevant variables, right? The same thing, let's see, maybe I can just jump back there. If you remember this slide, right? We constructed P of A, B, C, D, E, and we summed out A and D, right? Like in the continuous space, the sum is just an integral, right? And so what we're going to do in our case is we are just going to we're just going to construct the joint of all the actions, all the states, all the optimalities, and we're just going to sum out all the irrelevant stuff. So we're just going to say we're going to construct a joint over the current state, current action, all the future states, all the future actions, all the future optimalities, right? And we're just going to sum out. We don't care about future states and future actions. You just care about current action given current state and future optimality. So you're going to take all of these states and actions, you're going to sum them out. So this sum is over ST plus 1 T and AT plus 1 to T, right? And just if you just replace integrals with sums, it's the same logic as the previous. Yes.
Why is it integrated with respect to like ST? Sorry, I was kind of like lost there. Like,
Oh, yeah. So you're like adding. So this joint is going to be from AT to capital T, ST to capital T, OT to capital T. Right? Like this joint over here. This thing. It's like all of the time steps from now till the end for states, actions, and optimality. Right?
probability of like finishing this optimal trajectory.
No, it's just like you can if you just think of these as random variables, right? It's just the probability of like all of the random variables is a big joint distribution. Right? So it's like the joint distribution, what's the likelihood of this set of states, this set of actions, and this set of optimality occurring together?
Isn't that just the probability of a trajectory?
No, because it's also the probability multiplied times the probability of optimality. Right. So it's going to be probability of like it's this thing, right? If you look at this guy, it's like that thing multiplied by like it's essentially P of tau comma O 0 to T. It's like that thing. Okay. Sorry, I scribbled all over this page. But what I'm trying to get at here, don't think of it too deeply. What I'm trying to get at here is there's lots of integrals, and more importantly, there's an integral in the denominator. And if there's an integral in the denominator, it's very hard to compute, right? And so this inference query is very hard to compute unless you assume everything is Gaussian. If everything is Gaussian, then everything works out. It becomes a Gaussian filter. But if everything is not Gaussian, then this integral is intractable to compute. And so my point that the point I'm trying to make here is that this posterior inference query is not an easy one to compute in a continuous space. In a discrete space, you just multiply a big table, add up a bunch of stuff, you get what you want. In a continuous space, you have to divide by an integral. Division by an integral is always hard. Right? So the main point to take away here is we want to answer this posterior inference query. Given that you're acting optimally in the future, what is the likelihood of an action at a state? Right? But that posterior inference query is very hard to actually compute. Oh, sorry. Yes. Right. Okay, yeah, that's a good catch. Maybe an easier way to write this is just like make this a complete joint, not a conditional. Yeah. So you can just like multiply the numerator and denominator by P of SC. Yeah, that's a good catch. So it's a little more confusing that I've written conditional here and I've gone to a full joint. We can just write both top and bottom as joints. Sorry, I missed who was next. Go ahead, Andy, and that's perfect. This one. We're trying to compute the likelihood of action given state and future options.
I guess if policy takes like maximum.
So what I'm arguing here is that there's no maximization anywhere yet. We're just trying to answer the question of like, it's a posterior inference query. It's just like there's a bunch of events that are connected by probabilities. You're just trying to ask, if you knew that these events occurred, what is the likelihood that you took this action?
Okay,
So there's no maximization.
because only is treat log like we did.
But the problem is you have an integral in the denominator. How is that going to fix anything? You still have like the problem is, let's say you did a log here, okay? Then you have a log integral. A log integral is the worst thing in machine learning. Avoid log integrals at all times. Because the problem with the log integral is that if you approximate with samples, you get like a wrong estimator, like the estimator is biased. And so the problem with like doing it with samples, like you're saying, even with logs, you're saying like do this and like maximize likelihood, right? The problem is that it's like you have a log integral. A log integral is very hard to compute because the estimator is biased. Yeah, go ahead, bud.
Oh, this might be against me. Is there supposed to be a action, a variable in the denominator? Like the A of T, because basically the numerator and denominator is the exact same.
No. There's a it's a small t to capital T.
No,
Yeah. I looked it up. Yeah.
Why is integer for
Why? Oh, because when you're trying to like divide by a sum, right? Like the problem is that if you like divide by a finite sample, like imagine you only have 10 samples, right? Like in a numerator, if you have 10 samples and 100 samples, it like eventually becomes consistent. Right? If you have a denominator with 10 samples, like the normalization factor is way off. And it doesn't like you can show that it's not a unbiased estimate. So if you have like, basically if you have anything where you have an integral in the denominator or you have log integral, if you try to estimate it with samples, right? So if you have log integral or if you have like 1 over integral and you try to approximate it with 1 over sum, and then if you remember our like first few lectures, you can like try to work out whether the estimator is biased or not. You'll see that in both of these cases, the estimators will be biased. I can send you some resources after, but believe me for now that they're biased, and that's the problem. But yeah, it's a very good question. Yeah. I'm sorry. Oh, we're just trying to like, I guess what we're trying to do is we're trying to like compute this posterior in terms of entities that we know, right?
Okay.
And so what do we know? We know the joint distribution of all of the random variables because we can just multiply their conditional probabilities, right? And so we're trying to express this thing in a bunch of things that we know. So we're trying to express it in this thing that we know and this thing that we know, and then marginalize out things that we don't care about, right? And so the problem is I don't know how to measure future optimality unless they're conditional on future actions. And so you're going to condition on future actions and then marginalize them out. Okay, I'm going to keep moving so that we get through the next 45 slides. Okay, so what makes this so cool? Why am I so excited about it? It's because it gives us a single framework. Like basically, as I was just telling Taiwan, it's like a hard, like quantity to estimate, right, with samples, this posterior. The other thing that makes this hard is that you don't actually know P. Like you can only sample in the environment. Right? You don't actually know all of the things. You can sample from them, but you don't know them as a table. But what makes it so cool is that different approximations will give us like different algorithms. So as in, all we will do is we'll construct approximate algorithms from like the probabilistic inference literature, totally different literature. And we'll show that like approximations to getting this posterior will give us different algorithms that we've talked about from a totally different perspective. And so I think that's what makes it cool. And the nice part is if you can do this, then you can just design hundreds of new algorithms just by changing your approximation frame. And so it gives you a unified way of thinking about it. And then you can design new algorithms by just borrowing more things from probabilistic inference. Okay. So that was step 1. And let's go through our main tool, which is going to be variational inference. And we're going to then use it to derive policy good, computer learning, all of this stuff. Yeah. So then we need a break. Should we keep going? Keep going? Okay, let's get through variational inference and we'll take a break. So we said that this thing isn't trivial, right? Let's try to look at it in a concrete example, right? A very, very simple example. Let's say you had a latent variable model. So you have some latent variable z that's unobserved and some variable x that is observed, right? And so this corresponds to our setting here. You can think of this as x, think of this as z, okay? So it's like you have you're just trying to reduce it to the simplest case, but you have a latent variable model. You have z going to x is observed, z is unobserved, right? And so the query we want to ask is that if we know p of x given z, and we know p of z, right? You know the prior p of z, you know the likelihood p of x given z, like what is the posterior p of z given x? Right? This is just like a simplified analog to our previous question. It's like we know how to we either know these likelihoods or we know how to sample from them, right? This is reward, this is transition dynamics, this is action prior, and we want to answer a posterior inference query, right? In a similar vein, what we're going to say is that we have a z, it goes to an x, we want to answer p of z given x, right? It's just a simplification of the previous setting. We're going to use this to derive our algorithms. Everyone with me? Okay. So again, using Bayes' rule, p of z given x is p of x comma z divided by p of x, which is p of x given z times p of z divided by p of x, which is equal to p of x given z times p of z divided by integral p of x given z p of z, right? And so again, if this was a discrete space, this would be a sum, easy to compute. When it's an integral, you're trying to approximate it with samples, it's going to give you a biased estimator, right? And so trying to compute this is like hard because you can't really compute it with samples, and it's hard to do this in a tractable way, right? So we wanted like an easy function which I can sample p of z given x from. That's the posterior, or in our case, it's the policy, right? I want an easy way to get p of z given x so I can just like sample from it, so I can act in the world, right? And the problem with it is that you have this integral in the denominator, and it's like a huge pain to compute, right? And so what a bunch of these methods try to do, MCMC, energy-based models and score matching and variational inference, all of these are like approximation methods to try and approximate this posterior, right? So all of them are just different methods to say, you really don't want to, this is what you often call a partition function, right? And you really don't want to deal with partition functions. And so we're going to try and do approximate things to like sample from this posterior, right? And so MCMC is a way to do it with MCMC is basically construct a Markov chain whose stationary distribution is equal to p of z given x, and then you can get it from sampling. Score matching tries to, get rid of this denominator by measuring like grad log p of z given x. And variational inference is what we're going to talk about today. So we don't need to go into the details of any of these, but the main point is the posterior is hard to compute. And we want to compute the posterior in an approximate way. These are three different ways to approximate it. We're going to do variational inference today, right? But if you're interested, MCMC is very cool, and so is score matching. They're all just different ways of computing this posterior in a tractable form, right? And the goal is to say, given some evidence, what is the likelihood of your latent variable? And like find a way to sample from that p of z given x, right? And why does this connect to our problem of interest? It connects to our problem of interest because we care about this posterior inference query. We care about this, what is the likelihood of an action given a state and optimality? You can think of this as observed x, this is latent z. So we want to ask, what is p of z given x, right? It's the same problem simplified. Yeah, believe me, ish. Okay. So if we keep going, we're going to do variational inference. And what's the key idea behind variational inference, right? The key idea behind variational inference is you have this p of z given x. It's hard to compute in closed form unless you're Gaussian, right? What we're going to try and do is we're going to propose a q of z given x, which is as close as possible to p of z given x, but from a tractable family, right? So let's say p of z given x was this complicated distribution. We're going to try and propose a Gaussian distribution q of z given x, and then try to find the member of the Gaussian family that is as close as possible to p of z given x, right? And so the point is that you're going to try and approximate p of z given x by a tractable q of z given x, right? And if it's tractable, like it's a Gaussian or a mixture of Gaussians or something that you can sample from, then you can like take samples from your posterior, right? And so the whole point of variational inference is going to try and make an approximate posterior Q of Z given X, and try to make the posterior and the approximate posterior as close as possible. But this is tractable, and that tractable posterior is going to allow you to sample, right? And so in our case, if you go back to our case, it's going to say, we want to estimate P of AT given ST and O whatever, right? We're going to have a Q of AT given ST, and we're going to try and make these things as similar so that I can then sample from this guy, which is easy to sample from, like a Gaussian, right? Gaussian is easy to sample from. And so what variational inference will try and do is try and approximate this posterior with a Gaussian, or things that are tractable, and try to minimize the distance between the approximation and the true posterior. Does that make sense? Right? So we're, yeah. It will lead to the algorithms that we derived. Yeah. 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 Variational inference is also simple compared to the other ones. So the point of variational inference is we just want to find a tractable approximation Q of Z given X, right? And so we're just going to introduce some approximation. Let's just, for the sake of discussion, make it a Gaussian, right? So we're going to have a Gaussian. We're going to try and make P of Z given X as close as possible to Q of Z given X. But this is a Gaussian, and this is like hard to compute, right? Now, the natural thing to ask is, okay, how the hell are you going to make P and Q close if I don't even know how to compute P, right? So you want to choose a Q that is as close as possible to P, but I told you that P is really hard to compute. So if I don't know how to compute P, then how am I going to ever choose the right Q? The whole point is you want to choose a tractable Q that is as close as possible to the true posterior P. And we're going to do some mathematical gymnastics to make it tractable. Yeah. Yeah, we're going to get a lower. Yeah. Yeah.
Right. Just disregard this kind of up, but isn't this kind of similar to like the expectation maximization?
Yeah.
We get that.
That's right.
Oh,
Yeah, it's very similar. And so what we're going to do is we're going to, it is, you can like consider it to be an EM out. And so we can think of Q as our approximation to P, which is an intractable posterior. In our case, P is going to be our policy. We want to come up with an approximate policy that is as good as possible, right? As good as possible means the approximate policy or the approximate posterior is as close as possible to the true posterior. How are we going to measure closeness? Closeness is in terms of scale. We've used this a bunch of places. We just want to find the Q or the parameters of the Q that is going to be as close as possible to the true P. Right? But I don't know the true P. And so the question is, how do I make this objective tractable? And as Andy and Varun were alluding to, we're going to do some like lower bounding stuff to make it tractable. Right? So our goal is to find the best. Any questions? Okay. So remember, this is going to be a detour, but the detour is going to be worth it because then we can derive these glorious RL algorithms, right? And so what we're going to try and do is we're going to say Q is known, P is unknown, like you don't know how to compute it, but can we like construct an approximation? Okay. So we're going to do a little bit of Bayes rule gymnastics here. Okay? So we're going to start with the scale divergence. And then we're just going to say that the definition of the scale divergence is Q integral Q log P over Q, right? So the KL between Q and P is integral Q log Q over P. That's it. The definition of the KL divergence. Yep. Okay, so that's the first step. And the second step is that you're going to note that you're just going to use Bayes rule. So P of Z given X is going to be equal to P of X given Z times P of Z divided by P of X, right? Just Bayes rule. And so you're going to say, I took the definition of the KL divergence. But remember, we're just trying to derive a tractable lower bound. And so we took the KL divergence, we replace P of Z given X with the Bayes rule, right? And so now we have, like you can just add this as Q log Q divided by P of X given Z times P of Z. You divide by P of X, which means P of X goes up here, right? So you have Q times P of X divided by P of X given Z times P of Z, right? So all we did is we substituted in the Bayes rule. So definition of KL divergence substituted in Bayes rule, okay? And then you're just going to like separate that log out into two parts. The first part is going to be this Q along with this guy and this guy. Right, so it's gonna be, you're gonna take in QZ given X log, you're gonna take QZ given X from the numerator and P of Z from the denominator, okay? So all we did is we like here's a simple way to write it. Let's just like separate this log out into like all of its terms, right? I don't know. So we can say it's Q of Z given X times log Q of Z given X plus log of Px minus log of Px given Z minus log of Pz, right? That's just the expansion of the log. And then you're going to take this term, you're going to take this term and this term together. That's going to make your first term, right? And then you're going to take this term and this term together. That's going to make your second term, right? So all we've done is we've expanded the log and we've separated out the, that's it. You don't even have to follow it in real time. If you just believe me, you can go back to the slides and work it out, right? But the point is we just separated the logs. And now if you look at this objective, right, one important thing is that this integral is with respect to Z and log Px does not depend on Z. So it just comes right out of the integral, right? And so you can write this whole objective as, no, okay, yeah. You can write this whole objective as, the first term is just a KL divergence between Z given X and P of Z, right? This is the definition of KL divergence. So Q log P over Q, or Q log Q over P is the KL divergence of the first term of the KL divergence. The second term is the expectation of log P of X given Z sample from your posterior, Q of Z given X, right? So it's expectation Z from Q log P of X given Z. And then the last term is plus log P of X. Yeah.
Do we even care about the last term?
Yeah, we don't. It's a good. So all we've done is we've like taken this thingy and we've decomposed it into three terms. Now let's think about these three terms. As Alexei just said, we do not care about the last term. It doesn't depend on Z, right? We're trying to find the best, or it doesn't depend on Q at all. That's the more important point. It doesn't depend on Q. This point goes away. This point, we know how to sample from Q because it's tractable. We know the likelihood P of X given Z given to us. And we know how to compute the KL divergence. We know the prior. It's easy to compute. Prior is usually a Gaussian. And we know Q of Z given X, that's also a Gaussian, right? So everything is now easy to compute. And nowhere do we have our posterior, right? And so we never have to like actually compute this thing in closed form, right? All we have to do is we have to like minimize this objective. And now this objective, this term goes away. And all of these are in terms of things that we know. Right? Things that we know and things that are easy to compute. No integral in the denominator, no nothing. Right? No log integrals. It's always integral logs. Integral logs are better than log integrals, right? And so all we've done is we've converted this posterior KL divergence into these two terms. And this is often what you'll call your evidence lower bound or your elbow, right? So let's kind of like make it concise. So we've taken our KL divergence. We've said that it's the KL divergence between the approximate posterior and the pre-posterior is equal to the KL divergence between the approximate posterior and the prime minus the expectation of the log likelihood under the posterior plus some log Px. Yeah. And the whole point of this is now this objective is tractable, easy to compute. Yeah.
It's like, so X here is like R.
Yes.
And E is like, is it both are state or?
Both are say that.
Okay, so then when we say probability, is it like, at every time you do like this?
Yes. So it's basically like, if you remember that action prior we had, it's going to be like the action prior propagated through the through the transition dynamics of the environment. So it's like, if I wasn't trying to act optimally, what would the trajectory likelihoods be? Right. So the likelihood, the thing that you observe is that you're acting optimally, and the prior is like, what would you do if you weren't acting optimally? And so I'll connect this back to our problem in a second, but let's just like get through the rest of this framework. Right? So the point here is that I want to get an approximate posterior. This is tractable, and now this objective is all in terms of tractable quantities, right? And so let's skip through it. So if I want to find the best posterior, all I need to do is solve this maximum. I just convert from a minimization to a maximization with a negative. But if you want to solve this maximization problem, which says that you sample X from your data. I just added an expectation X outside. But you sample X from your data, you sample Z from your tractable posterior, Z from Q. And then you try to maximize the log likelihood of P of X given Z. Right? So in our case, P of X given Z is all known. Right? Those are the likelihoods in your environment. We'll get to what they are. But in cases where you're trying to find the posterior, what we said is we know this, we just don't want to compute that integral, right? And so everything is known. And so the first term is saying you sample X from your data, Z from your posterior, and then maximize the likelihood of X given Z. Right? And then you're saying, and you try to subtract the KL, which is between the posterior and the prior. Right? And so an intuitive way to think about this is that the first thing is doing maximum likelihood, and then the second thing is saying to stay close to the prior. So if you're, how many of you have heard of variational autoencoders, VAEs? Right? So VAEs are trying to do reconstruction. So they're saying go from X to Z and Z back to X, but keep the Z's close to the prior, right? It's like the same thing. You're saying this is reconstruction, right? It's saying that like you go from X to Z, and then you go from Z back to X. So that's reconstruction, and your maximum likelihood. And the second thing is just saying stay close to the prior, right? So in a VAE, you try to stay close to unit culture. In this case, you're going to stay close to the action prior, right? So you're just going to say maximize likelihood while staying close to the prior. Yeah.
Perhaps I'm a little confused, like, it seems to be that Z is completely unobserved, I'm so confused how we ever get anything from that.
Z is unobserved as in like, you know that there exists a random variable Z. And in our case, we know the likelihood term P of X given Z. So we don't know what the value of Z is, but it's not just like an abstract entity in the air, right? So in our case, for instance, let me forward a few slides. In our case, for instance, right, like these things are Z, and this is X, right? So you know what Z means, and you know how X depends on Z. You just don't know that given an X, what is the distribution over Z, right? So it's not unlike a VAE. In a VAE, the Z is like an abstract space. In this case, the Z is not an abstract space. Z is like a known space. You just don't know how to compute the posterior in a tractable way, right? So there's two different ways of, I won't have time to go through the slides here, but there's two different ways of thinking about this evidence lower bound. One way is like, you know this, and then you're just trying to compute this tractably, right? And the other way of thinking about it is you don't even know what Z is. Like in a VAE, you're just trying to maximize likelihood. You don't know what Z is. And that is a different setting where Z can be like an arbitrary latent space, right? So I think Z is almost a little confusing because we think of Z as a latent space. Z in this case is just an unobserved variable.
In our graphical model.
Yes.
What is P of Z represent? That's P of trajectory.
So that's the question that Ethan was just asking. Like it's going to be P of trajectory. Yeah. P of trajectory without optimality. Yeah, these are great questions. Okay, so we're just going to stick to view one. If you want to learn about view two, we'll go through it in the slides, but or go over my slides later. But all we're trying to do is we know P of X given Z. We know P of Z. We want to compute a posterior P of Z given X. It's just hard to compute because of all those integrals in the denominator. We constructed an objective which lets us compute that approximate posterior. You can just solve this with gradient descent, right? Like Q is differentiable. You can solve this gradient descent.
You're saying a loss function of this kind is what's common across these genes we call variation?
Yeah, yeah.
Why do we use the word variation or use the variation in the nth sense?
I guess, yeah, it's because of calculus of variation, because you're like introducing an approximation Q, and you're trying to like minimize the ratio of P and Q, or like you're trying to make P and Q as close as possible to each other. As in, like, what is your understanding of calculus of variation?
Little delta symbol, and then that's the variation.
Oh, in that sense. I guess in machine learning, often when you do variational things, you're trying to introduce an approximation Q, and then you're trying to make Q as close to P as possible. Right? And so here we're just trying to introduce an approximation Q and make it as close to P as possible. I don't quite follow why, I don't quite have a very clear explanation of how they're connected to calculus of variations. That's right. It does sound cool. Okay. Yeah. Okay, so what we did is we introduced a tractable, the thing you want to remember is this equation, right? This is like super important equations, evidence lower bound, or the elbow. And the elbow is just saying to find an approximate Q, you just solve this thing with whatever method you want, right? You want to just maximize this objective with whatever method you want, and that is going to give you the best approximate posterior, right? And so now we want to solve this posterior inference problem. We're just going to introduce a Q. We're going to solve this optimization problem, and we are going to get back to the best approximate posterior Q. And now we can use Q as like my policy, right? And so we're going to like try and relate this back to our problem. But the point is that you can think of, we had an intractable posterior. You have AT given ST and OT to T equal to 1. We're going to approximate it with a tractable posterior, Q of AT given ST. We're going to use this kind of objective with some terms substituted, and that's going to become tractable, right? So this thing was hard to compute. This thing is now easy to compute. You just have to solve this optimization. You can just use the gradient descent.
Why do we like lower bound? Because we remove the.
Because you remove the log features. Yeah. So the easiest way to think of the lower bound is that you could show that log p of x minus some PL of the posterior is equal to that evidence that term from last time. And PL diverge is always positive, which means that this objective is a lower bound of the log length. Right? And so that's why the evidence. Okay. But don't get confused by this thing. The main thing you want to remember here is that this gives you a way to compute a tractable posterior. Okay. So let's try and go back to our original problem, right? So we have this like difficult to compute posterior, and we want to approximate it by an easy to compute tractable Q, right? Now the nice thing about Q is you can choose any form that you want as long as it's tractable. Like you need to be able to do two things with Q, right? You just need to, maybe I have it somewhere. Okay, well, I have it in a later slide. But the main thing that you need with Q is that you need to be able to compute likelihoods from Q. So you need to be able to compute log Q, and you need to be able to sample from Q, right? So there are two things that you need from Q. So if you look at this objective, right? If you look at the evidence lower bound, you need to be able to sample from Q, and you need to be able to compute a KL divergence, right? So as long as you can choose any form you want for Q, as long as it satisfies those things, like more expressive forms make a better approximation, and less expressive forms make a worse approximation. Right? But we've taken a detour. Let's go back to our original problem. We want to compute the soft optimal policy, hard approximation problem. We want to use variational inference and approximate it with an easier choice of Q, right? And so we're going to remember that we had this simplified form and this complicated form, right? So we're just going to say that X here is all of the optimality variables. And we're going to say that Z is states and actions, right? And so substituting in X as optimality variables and Z as states and actions, we'll try and like rework out the evidence lower bound, and we'll show that it gives us all these RL outcomes, right? Everyone with me? So variational inference says it's an objective that lets me approximate a difficult P of Z given X with an easy Q of Z given X using this objective, right? We cast this posterior inference problem through variational inference, saying that X is optimality and Z is states and actions. That's it. Right? So variational inference is a tool for approximation of posterior. We're going to substitute X as observed, X as optimality, and Z as states and actions.
Does the fact we're underestimating is without the really makes the reward. But importance, is that good? Because then we can't, like exploit problems in the month.
Sorry, can you repeat that? The fact that we're using a lower bound? Yeah. I don't think so. Yeah, I don't think so. Yeah. Well, I guess if you're trying to maximize, you have to maximize the lower bound, right? And so if you're trying to maximize the likelihood of optimality, you have to like maximize the lower bound, you can't minimize the lower bound. So I guess for that reason. Okay, but let's substitute in what these things mean, and we will try and derive the next set of algorithms. Maybe we'll skip the break because I'm running short on time and I do want to get through some stuff, right? But the main thing to remember here is that we derive this evidence lower bound. Evidence lower bound gives me a way to approximate P with Q. Okay, and Q is tractable. And now what we need to do is we need to choose a choice. We need to choose a particular form of Q Z given X, right? So we said that X was optimality and Z was states and actions, but we need to pick a form of our variational family Q, right? And so we're going to show that for a particular choice of Q, you're going to rederive all these RLs. Okay? So just like we in like a variational autoencoder, you often have a neural net that takes an X and spits out the mean and variance of a Gaussian, right? And that's going to be your Z. We're going to choose a particular form for our Q. We can choose any form we want. It just needs to be tractable, right? And so the main things we care about is that you can sample from Q and that you can compute the KL divergence with Q. That's really all that we care about. Yeah. So we're going to choose a very particular form of Q, and we're going to choose Q to be the following. So we're going to say the likelihood. So remember, Q is a Q of Z given X, right? So Q of Z given X, you remember this, it's Q of Z given X. Z is states and actions, X is optimality, right? So we're trying to find a Q over states and actions given optimality. Yes? And so what we're going to do is we're going to like represent it in a kind of weird way. We're going to like say that the likelihood of the posterior is going to be the true likelihood of the initial state is going to be unknown, right? But we're going to say, and I'll show you why it's okay. It's going to be the true likelihood of the initial state times the true dynamics times the approximate policy times the true dynamics times the approximate policy times the true dynamics times the approximate policy, right? So simplified, it looks like the true initial state times the true dynamics times the approximate policy Q, right? So this is still an approximation. This part is approximated. These parts are from the true dynamics. And they're not known. You can only sample from them. You can sample from the initial state distribution if you reset. You can sample from the dynamics, but I don't know how to compute likelihoods. Yeah.
That first equality, should that be?
Because Q is our choice, right? Q is our choice of approximation. So we can choose whatever Q we want, right? So we're just trying to say that there's a posterior P of Z given X. There's a true posterior, and we're approximating it with our own choice of approximation. This is a particular choice of approximation, right? So it's like saying that we can choose whatever family of approximations you want. You can choose it to be these neural nets, so you can choose it to be these other things. You can choose it to be a product of certain things that you want. Right? It's just that different approximations give you different, different tightness of your bound.
So, okay, so we know the S0, yeah, PS1, so
Well, we know how to sample from them, but we don't know their likelihoods. Right? But the trick we're going to do is we're going to get a bunch of stuff to cancel. Just like model 3 we're going to get a bunch of stuff to cancel, and that's going to make our life good. But the point is that we can choose whatever family we want. We chose the family which uses the true initial state distribution, the true dynamics, and then our approximated policy. Right? So Q is like Q AT given ST is a policy. We don't know. We're going to learn it, right? But these are the true dynamics and the true initial state. Okay. And now this seems a little bit crazy because I said that we need to do two things, right? I said we need to be able to sample from it, and we need to compute the KL divergence. And we know that we can sample from these things, but like we don't know how to compute the KL divergence, right? And so if I said I wanted to be tractable, why did I use something that is intractable or unknown? And I'll show you that these things kind of cancel out. It'll be all tractable. And so the point is just the main point to remember is we had a Q of Z given X. We chose this form of approximation for it. And now we're going to substitute that into this equation. Right? So all we're doing right now is we're saying we're choosing a form of Q. We know what X is. We know what Z is. Now we know what Q is. And we know what P of X given Z is. And so we just substitute in here and try to find what the evidence lower bound is for control. Yes? So, okay, I can see everyone's a little lost, but let's recap, right? What we want to recap here is that we had this controller's inference problem. The difficult question we wanted to answer was P of AT given ST and optimality equal to 1. We said this is intractable, difficult to compute, integral in the denominator. Now we introduce this technique, variational inference. Variational inference tries to solve posterior inference queries through optimization by trying to find the best Q that can approximate an intractable posterior P of Z given X. Right? And it does so by optimizing this objective. Now, to optimize this objective and make this like match our problem of control, we saw that we can say X is optimality, we can say that Z is states and actions, and we want to find an approximate Q of Z given X, or an approximate Q of states and actions given optimality. Right? That's the thing we're trying to find. And now we needed to choose a form for Q, and we chose a very particular form, mostly to like cheat the math a little bit. But the point is we like chose this particular form, and we're going to like substitute this into here and show that it gives us our, like, we'll show that when you substitute this thing in here, it gives you reinforcement. Yeah. Which Q? No, it's not a Q. This is there's not a coincidence, it's your policy. So it's saying that like, this is the like Q of Z given X, right? And so this is your choice of like policy. So it's saying this is how you transition and this is how you act, right? So you're trying to find the best policy, right? So we're saying that it's the policy that acts under the true dynamics of the world. Right? That's the point. So let's kind of get through let me work through the derivation, and then I think the choice will make a little more sense, right? But the main premise is variational inference gave us a way to compute this posterior, and the posterior is the optimal policy. And variational inference gave us a way to compute this thing, right? And we're just going to substitute things in to compute this. That's it. Yeah. Okay. So what we're going to do is we're going to like we're going to use this form of the Q, right? We're going to use the form which has the true dynamics in it. There was two qualities we cared about. The first is that can you sample from it? And sampling from this Q is very easy. You sample an initial state, you sample the next transition dynamics in the world, you sample an action from Q rather than from a policy, right? And then you just keep repeating. So you can just think of Q as a policy, right? And sampling states and actions from this Q is just like taking rollouts in the environment. It's like sample a state, sample dynamic, sample action, repeat, right? And so this rollout is literally just rollout in the environment using Q as a policy, right? That's it. So there are two qualities we needed in Q. We needed to sample and we needed to compute KL divergence, right? And so the first quality is easy because you can just sample an initial state, sample an action, sample dynamics, and keep rolling out in the environment, right? It's RL, you can roll out in the environment. And so the first quality we know how to satisfy. The second quality, which is the KL divergence, is a little more tricky, but we'll show that it's not so crazy and everything cancels out, right? So this is our evidence lower bound. X was optimality, Z was states and actions, okay? And we're going to try and choose this choice of Q, right? So you can see that this is Z, this is X, right? We're going to choose this choice of Q, stick it into that equation, and hope for the best, right? Let's kind of work through it step by step, yeah? And so it's going to be a lot of symbols, but just aim to get the vibes, not follow the symbols too much. So that's your evidence lower bound, okay? I just like did a little bit of rearrangement. I just like moved one of the terms from the KL divergence here. It's a little easier to think about, but you can also write the evidence lower bound as log P of X comma Z minus log Q of Z given X, right? You just expand the KL divergence a different way. But this is the same thing as the evidence lower bound. Let's kind of build on that. And what we're going to do is we're going to substitute this thing in for Q, and we're going to substitute in the P's that we know exist in the environment, right? So we like define this graphical model. And we like talked a bunch about like there being true dynamics, there being like a P of OT given ST and AT, talked about an action prior, right? And so we know the true likelihoods in the environment. We know the Qs, let's substitute everything in. So the first step was you wrote out the elbow. The second step is that you like substitute in what X and what Z is, right? And so I stuck in X and Z. So it's going to be log likelihood of this stuff is Z. This stuff is X. This stuff is Z. This stuff is X, right? So this equation and this equation are the same, right? They're just substituting in Z and X, right? From here and here. Yeah, everyone with me? So the point is that we just had the elbow. We know what X is. We know what Z is. We substituted. That's it. Okay, let's keep going. Now, one thing to note is that the expectation is just like sampling from the environment, right? So it's saying sample initial states, sample actions from your policy queue, and sample next states from your dynamics, right? So the expectation is just like taking rollouts in the environment, the same way that we described in the last slide. It's just like sampling from queue is the same thing as sampling from the environment. They're like the same thing, okay? And so the expectation we're going to compute is just think of this as sampling from the environment, right? And everything else we just did a substitution of X and Z. That's it. Okay. So we haven't done anything. We just used the definition of the elbow. The next thing we're going to do is we're going to try and substitute in what we know for this term and what we know for this term. Okay. So we know, let's start from the Q term. We know that the Q term is equal to like initial state likelihood times transition dynamics times policy Q of AT given ST, right? And so that's just going to be the second term here. This log Q is going to be initial state likelihood plus transition dynamics plus likelihood of Q of AT given ST, right? We just took log likelihood of a product, right? We just sum of log likelihoods. So all we did is we took this thing, we took log on it, and gave us this term. Yeah. Now the first term is the likelihood of the joint states, actions, and optimalities, right? So it's like take all of the variables in our big graphical model and just like take the joint of all of them, right? So states, actions, optimalities, the joint of all of them, right? So can someone help me walk through what would this joint look like? Sorry, this joint. What did this joint look like? It's the joint likelihood of states, actions, and optimalities. So if you go back to the starting of the class, right? So yeah, so it's important to say it's going to be the product of the initial state times the action prior, right? Times the transition dynamics, but also times the likelihood of optimality, right? So if you remember our initial thing, we worked out P of tau and optimality, right? We said it's P of tau times P of optimality given tau, right? And we said that this thing was a product of a bunch of optimality terms, and this thing was a product of a bunch of dynamics terms, right? And so, as William was just saying, it's going to be the product of an initial state times action prior times dynamics plus log likelihood of optimal plus log likelihood of optimality, right? So you can think of it as like going back to our like graphical model. Where'd it go? It's going to be like this term multiplied a bunch of times. This term, you have an action prior and you have an initial state distribution, right? So like it's all of those terms multiplied together to give us the full joint. And so the point here is that we can write it as initial log plus action prior plus dynamics plus log POT given ST and AT. That's it. It's like take our initial graphical model and just decompose it into all of the terms, all of the like independent likelihoods, right? And so now if you look at these two terms, right, they're nice in that this and this cancel, this and this cancel, right? And then you know that P of OT equal to 1 given ST and AT is equal to exponential reward, right? Which means that you stick it into here, you just get reward. right? So all we've done is we substituted in likelihood, we substituted in Q, and likelihood is just a product of the independent terms. Q is our choice of Q. Um, and um, and then we just like know that these things cancel. And we know that these things cancel, and we know that this thing is X bar, right? And so sorry. We know that if you cancel these terms out, this becomes essentially sum of log probabilities of optimality, and there's going to be a residual minus log Q term. Okay, so like these terms all cancel. We said that the action prior is uniform, right? So uniform is a constant, you can get rid of it. And then we said that log probability is going to be exponential R, right? So it's just going to be this term. You substitute log or probability is exponential R, and then you recover maximum entropy reinforcement learning, right? Yeah, go ahead.
Do you have the action prior?
I said it to be a uniform constant. So what the action prior means that if you were not assumed to be optimal in the world, let's say you were just like messing around in the world, not optimal, then you are just acting uniformly. So it's important that we, like when you're doing goal-directed behavior, that is your policy. The policy is the posterior. So the policy is what is the action given state and optimality. And the action prior is just saying if you didn't know what you were doing, what would you like? What do? You just do random stuff. Right? Yeah. One other way of thinking about it is you can always kind of subsume the action prior into the reward. But just the easiest way to think about it is just think about it as uniform. It's just like a prior on what you would do if you didn't know what you were doing. Right? But essentially what we did through all of these gymnastics was we wanted to get the posterior. We didn't know how to get the posterior, so we turned to variational inference. Variational inference says you can get the best Q by solving this optimization. Now we showed that this optimization with all these substitutions comes out to this thingy. You substitute P as exponential R, and then you just get maximum entropy R out, right? And so now what you've done is you've shown that this is sum over rewards plus like minus log Q is entropy, right? And so you can show this is sum over rewards plus entropy. And so if you remember like our lectures on policy gradient, it's just like, if I just maximize this objective, this is the evidence lower bound, right? I can just maximize it with gradient descent. If I maximize it with gradient descent, then it just becomes maximum entropy policy gradient, right? So it's just saying it's policy gradient as usual, right? So we can optimize this objective with whatever we want. Let's say we did policy gradient descent. It's policy gradient plus an entropy term. That's it. So it's like soft policy gradient, right? So let's recap what we did. I've made recap slides, so this will hopefully help us, right? And so we wanted to we introduced this graphical model. We added these auxiliary variables where the likelihood is equal to exponential reward. Yeah. And then we said that the optimal policy is P of AT given ST and all the future auxiliary variables being optimal. So it's what is the likelihood of the action given the state and future optimality. We didn't know how to compute that, so we had an approximate posterior Q. And we said approximate posterior Q is going to come from variational inference. Variational inference is going to make this hard, intractable approximation into an optimization, right? And then we substituted a particular form of Q using the true dynamics in. And then you show that the variational inference evidence lower bound is exactly equal to maximum entropy RL, right? And so what's cool about it is we started with this like variational inference, which seemed totally unrelated, and then you applied it to this posterior inference problem, and then you get maximum entropy RL. And so, and then the point here is now you have this objective in an evidence lower bound, right? You're trying to find the best posterior. If you're trying to find the best posterior, you just want to maximize this objective. You want to use gradient descent to maximize it. You just get maximum entropy policy gradient, right? And we've run out of time, but the next time we can show we can also derive Q learning and model-based RL from the same perspective. Okay, so that was a lot. I told you it's going to be the hardest lecture, but hopefully this kind of made sense. Okay, please come chat with me if you want to talk about it more. All right, thanks.
That was fun.
Yeah, it's a journey. I think I was like a little nervous to do this lecture, but it's like I find it super cool, so I wanted to
I think it would have been lost, but we have like, we acknowledge like the variational inference, but yeah.
Think of variational inference as like is a difficult problem of computing integrals, and you're replacing it with an easier problem of optimization.
I learned it with PPCA. It's probabilistic PCA.
Oh,
Factor analysis.
yeah.
That's where I was coming from, so I was like, oh, that looks like somewhat similar when
Yeah.
you did it. My teacher at Hana used to name X to Z, or Z to X.
Yeah.
So I was like,
Right.
how the- Kind of project and all the salaries kind of like overlap.
Yeah, of course.
But if anyone else is faster.
I have a cutoff at 1:15, but that should be enough, right? Yeah.
Theoretical simple question.
What's up? Hello.
Formula.
Yes.
Is in the